Okay, so today I wanted to continue the topic of my previous talk and explain a bit more the motivation of homotopy theory and higher differential geometry that comes from classical and quantum mechanics. So I will do it along the lines of the introduction to Schreiber's book about differential cohomology in smooth cohesive topoi. First, let me just quickly explain rigorously what are gerbes. So last time we used them a lot, and I just said that gerbes are like higher bundles. But there is actually a pretty concise way to understand what are gerbes. So first, let's observe that if we have a pre-sheaf of simplicial abelian groups, then we can apply the Dalton correspondence object-wise, and we will get a pre-sheaf of chain complexes of abelian groups. But chain complexes are very interesting because for chain complexes, we have obviously a shift operation. So we can shift the chain complex 1 degree up or down, and we can iterate this operation. And that means that we actually can shift any sheaf which is valued in simplicial abelian groups. So, for example, let me just explain an important example where this procedure applies. So assume that we have a pre-sheaf of simplicial abelian groups. Then this suspension operator, which is a +1 shift on chain complexes, actually coincides with the de-looping operator on simplicial, on pre-sheafs of simplicial abelian groups. So obviously, if we have a pre-sheaf of groups, then we can apply the functor of the classified space at each level, and we will obtain, in general, a simplicial set. But as it turns out, if we have simplicial abelian groups, we will actually obtain, once again, a simplicial abelian group. So another way to define this operator intrinsically to sheaves of simplicial, pre-sheaves of simplicial abelian groups without passing to chain complexes is by taking this groupoid. So we can take an action of this pre-sheaf on a point, and then we can take the action groupoid, and we will obtain a simplicial abelian group. So in general, this doesn't work, but if the initial group was A, then this quotient or the de-looping is once again a simplicial abelian group. Why? Well, because we can define the group operations at each level. But for this to work, we need this group to be abelian. So if we have just G times G, etc., we can define the group structure at each level in a coherent way. So obviously, we can say that at each level we have a group which is just a product of the group we're de-looping. But for this to become a simplicial group, we need it to be abelian. And when it is abelian, we actually get an operation which from one abelian group or from one simplicial abelian group produces another simplicial abelian group. And that's the essence of this operator B. Okay, so we can iterate it. We can take Bn of a pre-sheaf of simplicial abelian groups. But then, as it turns out, if we just take some abelian group A, for example, so A can be just a circle, Then we can take the iterated d-looping of A, and we will once again obtain a simplicial abelian group, or, well, a simplicial pre-sheaf of simplicial abelian groups. So obviously, if we have a group, then we can associate to it a constant pre-sheaf. And then if we apply this iterated d-looping, we will once again obtain a pre-sheaf of simplicial abelian groups. And then we can take the derived map in space from X to this B and A. We will usually denote it just by this square brackets. And we will obtain something that is known as n-1 gerbes. So the idea is that if we have n equal to 0, then we should take the derived map in space from X to A. So A is just B0 of A. And this is just the space of A-valued functions on X. And similarly, 1 gerbes are A bundles because we take the derived map in space from X to the classifying stack of A. And so on. So we have this hierarchy of gerbes.
Sorry, recall please. So what is A? A is U of what?
So that was just an example, but it can
in the previous slide.
Yeah. U1, just the circle group. So.
Okay.
That was just an example of abelian group that we can d-loop and obtain something interesting. So, yeah. So for example, when we're dealing with these problems from physics, we usually take A to be equal to U1, but in general, it can be any abelian group. Yeah, so we have this hierarchy of gerbes. So at level 0, we have functions valued in this abelian group. At level 1, we have bundles. At level 2, we have proper gerbes. At level 3, we have 2 gerbes, etc. And the general description is that just gerbes are just maps from a space to this iterated d-looping. So, of course, we can define it using some explicit constructions. So, for example, of course, we can define bundles as something which is locally trivial and has structure group A, etc., etc., etc. But actually, we can think of bundles as just maps from the base to this classified space. And that's a very useful point of view because we don't need to do a lot of technical work when we're dealing with this kind of definition. So gerbes are just maps from pre-sheaf, sheaf to this iterated d-looping stack. That's the general idea. Okay, so now let me describe the local goal that we have for today. So first of all, last time we learned how to integrate differential cocycles of degree p plus 1. So we integrated them over the whole space-time, and we obtained the action functional, which is a function. And we know that the function is the 0 gerb. So the reasonable thing to do is to try to integrate differential cocycles over some submanifolds, and instead of 0 gerbes, obtain some higher gerbes. And that's precisely what we will try to do today. So assume that we have a submanifold inside of the space-time sigma, and assume that it has codimension k. Then our goal for today is to try to understand how to integrate a p gerb over M and obtain a p minus k gerb. So our first order of business is to understand how this works in codimension 1. So when we have a hypersurface inside of our space-time and we want to integrate over it and obtain a one gerbe, which is just a bundle. So instead of an action functional, we will sort of have an action bundle. Okay. Are there any questions so far? Okay. There are no questions. Let's proceed. So first of all, let's describe the following operation on differential forms, which is called transgression. So first of all, assume that we have a manifold sigma. Then we can take the mapping space from sigma to the classified step of differential p+2 forms, and this thing forms a sheaf on manifolds. So the sheaf structure is given by this classical construction that when we evaluate it on U, we just take p+2 forms on the product U times sigma. So then we have the operation of fiber integration. So we have this trivial bundle, and we can take fiber integration with respect to this component, and then we will obtain a homomorphism from differential forms on the product into differential forms on this manifold U. Of course, this construction is factorial, which means that in actuality, this operation of fiber integration gives a morphism from this sheaf to this sheaf. And now we can define a transgression of differential p+2 form on some smooth space X. How we do that? Well, we just take the composite of two operations. So first of all, we take the mapping space from sigma to X, and we apply it to this morphism alpha. And then we take the operation of fiber integration, and we obtain composite morphism from the mapping space from sigma to X into differential p+2 minus d forms. So let me reiterate, this transgression operation takes as an input p+2 form on some space X, and then it constructs a p+2 minus d form, where d is the dimension of the spacetime of sigma, on the mapping space from sigma to X. So in a sense, it's a pullback of a form on the nose onto the whole mapping space. So there is, of course, a more classical approach to this definition. Assume that we have a p+2 form on X, as before, and assume that we have a manifold of dimension which is less or equal to the dimension of the space X. Then the transgression, which is in this case denoted by this tau sigma, is such a differential form on this mapping space that when we restrict it to one-dimensional family of morphisms from sigma to X, we obtain this thing. So if we have this one-dimensional family of morphisms, then we can pull back along this family, and then we can integrate over sigma. And this thing should be precisely the restriction of this form onto this curve in the space of maps. So that's, I guess, more explicit way of stating the same thing. Okay. So now, obviously, we want to prequantize the notion of transgression, as we do with everything. And this works as follows. So first of all, of course, we have this map, which is just a fiber integration. Then we can take transgression. So we apply this composite, and we end up with a map from the mapping space into this classifying space, which is just, as we saw earlier, it is just a gerb on this mapping space. So now let's recall what we had last time. So last time we had this local Lagrangian, which is just a map from the field bundle to horizontal p+1 forms. Then if we apply transgression to this local Lagrangian, we will get precisely the action function. So that's very nice, I guess, because we define this purely geometric operation, which reproduces the construction of the action functional that we had last time. Okay. So now another classical object from, I guess, classical mechanics, notion of a Cauchy surface. So if the codimension of a submanifold is 1, so we have a hypersurface inside of the spacetime, then we can take, well, I guess we can take it for the submanifold of any codimension, but we do this in the case of codimension 1. And we take this infinitesimal normal neighborhood of this hypersurface inside of the spacetime. Recall that by this E curly we denoted something known as shell, but that's just the space of solutions to the earlier Lagrange equations when we consider them as a morphism in a category of PDEs. So we know that, well, I guess sheaves on PDEs, but we know that we can embed this field bundle into the category of PDEs as solutions to the trivial PDE, which is just equal to 0 on all sections. And then we can consider this category and we can take a kernel in it. So we have this early Lagrange morphism. We take its kernel, and that's basically the locus on which our theory lives. So if sigma p is a Cauchy surface, sorry, let me explain what is a Cauchy surface. So that's basically the definition. Sigma p is a Cauchy surface if when we take the mapping space from sigma I denoted by sigma p+1 so that we remember its dimension, but that's just the whole of the space-time. If we take morphisms from sigma to E, so these are just solutions of the equations of motion, possible configurations of our system. So yeah, obviously, if we have such a morphism, it defines a classical state of a system. Then we say that sigma p is a Cauchy surface if this space is equivalent to morphisms from the infinitesimal normal neighborhood around sigma p into E. So basically, what that means? That means that a classical state of a system or a trajectory of a system is uniquely determined by values of derivatives on the surface. So if we know that I don't know. We have this surface inside of the space-time, and we know that I don't know. We have some particle, and we know that the derivative of its so its velocity vector is given. Then we know the trajectory. So that's just some very stupid example, but the idea is that a surface is called a Cauchy surface if we can recover the trajectory of our system from all derivatives on this surface. Of course, we can't assume that a Cauchy surface always exists. And kind of, if we do, then this means that we want to forcefully split our space-time into the product of Cauchy surface and an interval, for example. So we won't assume that we necessarily have a Cauchy surface inside of our space-time. But nevertheless, it's a somewhat useful notion. So I put it here. Okay. So now let's define what is a phase space. So first of all, as we saw earlier, the set of such sections gives us classical trajectories of our system. And as I said before, usually trajectories can be recovered from first derivatives on this hypersurface inside of the space-time. And in this case, the phase space is actually just the cotangent bundle of the mapping space from this hypersurface into the field bundle. So that's just a reformulation of this statement that trajectories can be recovered from first derivatives. So assume that we have a certain configuration, and we have its first derivative, so it means that it's a vector in this cotangent bundle. But then this means that we can recover the trajectory itself. So then this means that we have this equivalence between sections over the infinitesimal normal neighborhood of the Cauchy surface and over Cauchy surface and this cotangent bundle. But we won't assume such yeah.
So what is a smooth structure assumed, or what is the notion of tangent bundle in this case?
Oh well, just as usual, since this thing is a sheaf, and the tangent bundle is also a sheaf or cotangent bundle, because obviously if we have a manifold, then we can take its cotangent bundle. But then if we have a sheaf, then we just take natural transformations. Not exactly natural transformations. We take the internal Hom in the category of sheaves from F to T upper star. And since this thing is also a sheaf, we obtain the cotangent bundle.
Okay.
Yeah, that's the beauty of this approach, that we don't need to care about some explicit smooth structure on possibly infinite dimensional space of maps. We just formally apply this shift theoretic machinery, and we recover the notion of cotangent bundle. Okay. So in some very classical cases, it is said that the phase space of a system is this cotangent bundle. Of course, we're not in the classical case, and therefore we will refrain from such notation. And instead, we will denote, so we will call a phase space another object. As we saw, as I said earlier, in general, we don't have this equivalence. And so instead, we say that a phase space is just this sheaf. So what is this notation? Well, we just consider maps from sigma to E over sigma or sections, since here we have the identity map. So that's just the sheaf of sections. And this thing is called a phase space, and sometimes it's called a covariant phase space. The adjective covariant here just means that this phase space is invariant under automorphisms of sigma. So in a sense, it's a principal difference between this description of a phase space and this description of a phase space, because here we choose a splitting of our space-time. So we choose some hypersurface, then we choose a normal direction, and then, well, not just normal direction, the whole infinitesimal neighborhood, but nevertheless, it means that we have some, some external structure. So we don't just have this space-time, we have some distinguished surface, and we're looking at sections over the surface. But here we can act by the whole diffeomorphism group of the space-time, and this construction is preserved. So that's why it's called covariant phase space. Okay. So now let's recall let's introduce another important notion, that of a variational bicomplex. So first, let me just say some very intuitive thing about variational bicomplex. The basic idea is that if we have a configuration, then we can study its behavior in, well, if we have some family of configurations, then we can study its behavior in two ways. So we can study how it varies over the space-time, and also we can study how it varies if we pass from one configuration to the other. So since a configuration is just a section, we sort of have a vertical differential, which measures the change from one section to the other. And we have a horizontal differential, which measures how a section changes along the space-time. And that's very, very crude idea of what a variational bicomplex should be about. But let's give a proper definition. So first of all, consider a Durand complex of the jet bundle, then it is naturally bigraded. So since we have the degree of the base and the degree of the fiber, it is bigraded. Then the Durand differential on this bicomplex splits into the vertical differential and the horizontal differential. So the vertical differential sometimes is called the variational differential, and the horizontal differential is just called the horizontal differential. So as I said, these straight measures change along the space-time, and delta here measures change under the change of configuration. Okay. So if we have a field bundle over our space-time, then we have the following pullback construction. So sections of this field bundle, or just, well, any bundle, it's just a very general construction, are entire pullback of fiber actually of this map. That's just very general definition of a section. Then we can take the de Rham product, the de Rham complex of this product. Since this is also a sheaf, we have a de Rham complex on it. And we have a splitting of a differential once again, since it's a product. So we have a differential along sigma, and we have a differential along the space of sections, delta. Then we have a natural infinite extension of a section to a section of the jet bundle. So just take all the derivatives. Then we have an evaluation map from the product of, well, yes, it's not a very good notation. So let's denote it like this. So from a product of the basin times the space of sections of the jet bundle, and then we can evaluate each section at this point and obtain a point inside of the jet bundle. Now, obviously, this can be done in a case where we don't have any points, but the idea of this map is like this, and we can, of course, do it formally. We have this pairing, which maps this product into the jet bundle. Then we can take the composition, the pullback with respect to the composition of the infinite jet extension, and the evaluation map. And we will actually get a map from the de Rham complex of the jet bundle into the de Rham complex of this product, and it is an embedding. So this subcomplex, this is a subcomplex, and it inherits by gradient from by gradient on the de Rham complex of this product, and precisely this complex is called the variational bicomplex. Okay. So now we can apply a very similar thing to category of PDEs. So first of all, recall that if we have a bundle over a manifold, then we can represent it as a trivial PDE, which is identically zero on all sections of this bundle. And then we can also consider the following moduli stack, which is characterized by this property. So for any bundle over sigma, the sheaf of maps should be equivalent to this sheaf. So these are just closed p+1 forms on the jet bundle. Yeah, so I just spelled it out here. So this equivalence defines the moduli stack on this category of sheaves over the category of partial differential equations over sigma. Okay, so now this variation.
Sorry, this is by definition or some statement?
Yeah, that's just the definition. So if you have a moduli stack, then it is defined by this property that its value on something is equal to something. So that's the definition. Okay. Yeah. So then if we have these definitions and this idea of what is a variational bicomplex, we can consider a universal variational bicomplex, as we always do. If we have some functorial construction, we can take its sort of classifying stack and obtain just a sheaf on our category, and maps to this sheaf give the values of this factorial construction. So that's precisely what we do, and we obtain this universal variational bicomplex, which looks like this. So so we should have closed P2 forms. So now these two gradients are just two gradients with respect to differentials d and delta. And this is the moduli space of forms such that when we integrate it over if we integrate it over sigma p, which is a hypersurface outside of our spacetime, we obtain a closed 2 form on the space of sections. So the word pre-symplectic here just means that we have any closed form. So just recall that a form is symplectic if it's closed and non-degenerate, and it is pre-symplectic if it's just closed. Okay. So now we will have a sort of strange aside about pre-symplectic structure on the phase space of a mechanical system. So why is it strange? Well, because at the very end, we will see that in classical mechanics, this is a very trivial statement. But since we have this very, I don't know, unusual definition of phase space, we want to show that there is indeed a pre-symplectic form on this phase space. So how does it work? Well, assume that we have assume that we have a form like this. Then when we integrate it over a hypersurface, we obtain a 2 form. We obtain a current on the spacetime valued in 2 forms on the space of sections. So the word
sorry, could you move to the previous slide?
Yeah.
What is the connection between this sequence and the form omega?
The form omega is an element. Well, it is an element of this
okay,
thing.
I don't understand what is the significance of the previous sequence. This is
so that's the universal variational bicomplex. It's okay. A sort of explicit description. As much as anything that we do here can be explicit, but that's the description of sort of first several degrees of the variational bicomplex. So like degree 0, 1, etc.
Okay, and the point of this slide is about what?
So yeah, that's a great question. Well, I guess I just wanted to explicitly describe the variational bicomplex, and I mean we will sort of need it later. I don't know.
Okay, thank you.
Yeah, that's a great question. I mean, just a nice formula. I don't think that there is very deep meaning behind this slide. Okay, so the integral of this form over hypersurface is a current valued in two forms on sections. So a current is just a generalized function. So we want to show that actually this current is canonical. So first of all, this is not just any two form, it's a closed-to form. And therefore, it's a presymplectic current. So as I said earlier, presymplectic just means closed. But also it is canonical, meaning that meaning that in a sense, it is uniquely determined by our equations of motion and yeah, our equations of motion. Okay, so assume that we have a local Lagrangians, which are just defined on some covering family over E. So these are E+1 horizontal forms. And we want to lift them onto the first stage of our bicomplex. So I guess that's another reason why the previous slide was useful. So we want to consider a lift to the previous stage. And actually, this lift, if it exists, is given by the following sum. So we have this form Li, and we have this form θi, such that when we take the variational derivative of or variational differential of Li, we obtain the early Lagrange form with respect to local Lagrangian Li. And then we will get something like this. So we have the first two stages of variational bicomplex. We have our shell, which is just the kernel of early Lagrange in the category of sheaves on PDEs, and we will have this lift. And then we will have the following commutative diagram. So here we will have these forms omega I, which are horizontal differentials of theta i's. And here we have just the usual inclusion of a shell into the field bundle. So that's how a lift of local Lagrangians to the first stage of variational bicomplex can be accomplished, and this form Li is called the Lepage form. They will become important a bit later. Okay. So now let's consider the differential of this lift. So first of all, how it looks. So by assumption, if we take the variational differential of the Lepage form, we obtain the early Lagrange form. So we have this part. Then we have with respect to the horizontal differential, the Lepage form should vanish. That's why we had this some splitting. And so additionally, we have this term here. So we have theta I plus something which is obviously annihilated by dh. So since we assume that theta I lives in this, lives in this, it means that we can add some boundary, but in principle, everything here is defined by theta I. So we add the horizontal differential of theta I and we subtract. We add it and we subtract it. And also we have the vertical differential. So I sometimes will alternate between the notation vertical differential and variational differential, but these are the same thing. And also, I guess here I should write it like this. So we take the total differential of the sum, and it splits like this. So at the end, we get the Lagrange form with index I and the vertical differential of theta I. And we put by definition that the vertical differential of theta I is this form omega I. And so up to the boundaries of horizontal differential, so this term, theta I is uniquely determined by the Lepage form, because obviously we have this equality, which means that theta I up to 18 boundary is uniquely determined by the Lepage form and the early Lagrange forms which we have by assumption. Okay. So now assume that we have a P2 form omega on the jet bundle, such that when we restrict it to elements of our covered family, we get forms omega I. And such a form is called a presymplectic current. So then we can use a transgression with respect to sigma p inside of sigma p plus 1, so our co-dimension 1 hypersurface. And we get a presymplectic 2 form on the mapping space. So just by a usual formula that we take p plus 1 and we we take p plus 2, then we subtract p. So if you remember, we had this sigma d inside of our manifold X, and then we subtracted d. So in this case, we have a p plus 2 form. We subtract p, and we end up with a 2 form on the mapping space. So in this case, it was in this case it was sigma p, and we obtain a 2 form on this mapping space. And since it is our phase space and we obtain a closed 2 form, then this precisely shows us that we have a canonical presymplectic structure on the phase space. And in classical mechanics, it's a very trivial statement, because in the classical case, first of all, we have a Cauchy surface, but actually we have much more. We know that trajectories of our system are is uniquely determined by first derivatives. So the phase space is actually this cotangent bundle. And as many of you probably know, a cotangent bundle of a manifold is naturally a symplectic manifold. Because we can define a canonical form omega on this manifold by taking the following thing. So we have a pair which consists of one vector and one covector, and another such pair, and then we can just evaluate the first covector on the second vector and subtract the second covector on the first vector, and we obtain a symplectic structure. It's just I don't know, one of the first results from, I guess, any course that has something about symplectic, even symplectic forms. It's basically a result from linear algebra that on the vector space V plus V star, we have a canonical symplectic form. And so, in a sense, we used very hard and elaborate technique to show that we have a symplectic or presymplectic form on the phase space, which in the end, in the classical case, just reduces to this easy statement. But of course, there are cases where all this hard work is justified, where we don't have a phase space in such a simple form, and then we of course need something more powerful than just a cotangent bundle of some manifold. Okay, so now let's return to the question why this current that we defined is canonical. So we claim that it is actually a conserved current. What is a conserved current? Well, it is a current, or just differential form, in fact, such that its horizontal differential, when restricted to this shell, which is just solutions of our equations of motion, is equal to 0. So in very crude terms, that means that if we move around a little bit on our space-time, this current doesn't change. That's the meaning of this condition, that the horizontal differential is equal to 0. So if this holds, then omega is independent of of the choice of the hypersurface inside of our space-time. So assume that we have two hypersurfaces, d incoming and d outcoming of sigma. Then the difference between forms omega outcoming and omega incoming, which are obtained by transgression with respect to this hypersurface, is equal to 0. So this condition that it is equal to 0 is the result of the fact that the horizontal differential is 0, but it sort of holds in some cases. So if we're working with manifolds, it does hold, and if instead of manifolds we consider, for example, derived manifolds, then it is not equal to 0, but it is a boundary. So it's homologically equal to 0. It is a boundary of this another differential, but I don't want to discuss it in great detail. I just want to make this small aside that in some cases it's not strictly equal to 0. It's equal to 0 up to some boundary. Okay. So now let's discuss prequantum field theories in full dimension one. So first of all, consider the classifying stack of Lepage P+1 forms, maybe P+2 forms, P+1 forms. Yeah, I think P+1. Yeah. Of Lepage P+1 forms. So just by definition, we would say that so the values of this sheaf on some manifolds should give us sorry, not on our manifold, on our on some bundle over sigma should give us all possible Lepage forms for this bundle. So Lepage forms are given by such lifts. So that's precisely the condition on this stack. So we obtain this general picture that we have this hypersurface. We have some classical state, which is a section over this hypersurface of this shell. So a classical state is basically a certain state of initial conditions from which we can then derive our trajectories. Then we have this phi s, which are solutions of the equations of motion, which, as we saw during the previous talk, it's just a section. Well, it's just a lift along this inclusion of E curly inside of E straight. So phi is just some configuration, and phi s is a factorization of phi through E curly, meaning that this is not just some configuration, but it's actually an optimal configuration which solves our local equations of motion. Then we have this classifying step of Lepage forms or Lepage gerbes, which maps into early Lagrange gerbes. Once again, trivially, because by construction, Lepage forms were supposed to be a lift of early Lagrange forms. And so at the universal level of classifying stacks, we have this map from classifying stack of Lepage gerbes into the classifying stack of early Lagrange gerbes. Then here we have the prequantization of early Lagrange equations, which we described in the previous talk. And here we have the prequantization of the Lepage forms. So prequantization just means that we obtain a lift from here to these stacks. So it's basically a lift along the curvature map. And obviously, yeah, here we have curvature maps, which from these prequantized Lepage forms or prequantized Lagrange forms give us just forms. So basically, prequantized early Lagrange forms are like connections on principal bundles, and early Lagrange forms are just forms. So curvatures of connection, and similarly for Lepage forms, or well, Lepage gerbes. Okay, so that's, I guess, just a general picture of prequantum field theory in closed dimension one. And now, so we have this diagram. Now we can apply the translation functor to the entirety of this diagram. And what we obtain is the following diagram. So if we, one moment, yeah, if we hit the appropriate parts of our diagram with this transgression factor, I mean, it's kind of messy, I guess, but I think it's probably somewhat intelligible, although I'm not sure. I mean, well, yeah, so basically we need to apply this transgression function to this diagram here, and we obtain a diagram like this. So we have these spaces of maps. We have transgressions of our Lepage forms here. We have the fiber integration along sigma p, which produces from a form like this, a form like this. So if we integrate over sigma p, then it can be seen that we annihilate the appropriate dimensions, and we end up with a two form like this. And similarly, if we apply transgression to a map from the infinitesimal normal neighborhood of a hypersurface into our shell, then we end up with, well, basically with a connection. And analogously, if we apply transgression like this, then we end up with a canonical close to form, which is precisely the curvature of this connection. So in a sense, that's the promised generalization of the case of an action functional. So now instead of a function, we obtain I don't quite like this notation, but we obtain a map into the one-fold dilution of our abelian group, which is isomorphic to the circle group. And instead of a function, we obtain a bundle. So for the functional, this transgression reproduced just a function. So one form and a function. And in this case, it reproduces a connection and a two form, which is a curvature of this connection. So in a sense, we achieved success in our local goal to be able to integrate over some submanifolds of positive low dimension, albeit only for codimension 1 for now. But still, we integrated a differential Pope cycle, and we obtained a gerbe or a bundle in this case. So there is that. Then we can define the following theta small as transgression of this connection form theta large, and so theta large, as I said earlier, is the connection with respect to so a connection on a bundle with structure group R mod Z with quantum parameter H. And the curvature of this connection is precisely this form omega small, which we described earlier. And theta large can be thought of as the transgression of the prequantized bundle theta small. So we have this bundle, and theta large is the transgression of theta small, meaning that it was a genuine form on it was a genuine form on E. Okay. So here is the universal picture, sort of what we did earlier. So assume that we have a shell, we have the field bundle, then we have this connection form here. We have the prequantized Lepage form here. Sorry, I said something very stupid, not Lepage, it's just the prequantized early Lagrange form. Then we have curvature here, and we have curvature here, and then we obtain well, this higher prequantization that we sort of described earlier is just a map from the classifying stack of Lepage forms into this classifying stack of well, not Lepage forms but Lepage gerbes into the classifying stack of just well, of just gerbes. Yeah. So that's nothing new. It's just a reformulation of the previous diagram that we had here. So in a sense, I've just removed the parts which are not universal, and we ended up with parts of this diagram which correspond to classifying stacks. Yeah, okay. So yeah, these are early Lagrange gerbes, which correspond to horizontal forms. Okay. So the idea is that if we now apply the transgression to well, so now we can consider a submanifold of arbitrary codimension in theory, and we can apply this transgression operator to transgression functor to this diagram. And what we end up with is just the hierarchy of gerbes. So we have like p+1 gerbes, and then we apply this transgression functor, and we get p+1. Sorry, we get k gerbes. So I am cringing a bit here because the term k gerbes is not very adequate, because one gerbes are supposed to be gerbes, but in our terminology, one gerbes are actually bundles and two gerbes are gerbes. But I mean, if you think of gerbes just as classes of maps from some sheaf into the classifying stack, then when I'm saying k gerbes, it just means that n here is equal to k. Okay. So, for example, if k is equal to 0, then we end up with 0, 0 gerbes, which are in this terminology are just functions. And when we apply these to our diagram, it means that we just end up with the map which is defined by the exponential of the action functional. And if we apply transgression for a hypersurface, so the codimension is equal to 1, then we end up with something like this. So we have after transgression, we obtain, well, after applying transgression here, we obtain this thing. So we have this prequantized bundle on the space, on the phase space. Then we obtain this canonical presymplectic form on the phase space, and the curvature of this prequantized bundle is precisely this presymplectic form. So, yeah, that's what we wanted, and that's sort of what we got. So now let me just state another local law that we have here. So we sort of kind of very poorly, I guess, just me, understand how integration over some submanifolds of positive codimension works. But now I want to show how we can describe automorphisms of such structures. So, for example, we have some early Lagrange, prequantized early Lagrange form, or we have some early Lagrange gerbe, or we have some Lepage gerbe. And the question is, what are symmetries of such a system? So it's I guess it's a natural question that if we have a physical system, what are possible symmetries? And this second part of the talk will deal with a description of such symmetries and with its relationship with classical theorems about symmetries of physical systems. For example, Noether's theorem, which states that each symmetry has a corresponding conservation law. And this, as it turns out, it is possible to formulate it in these terms and see that actually each symmetry in the sense has a corresponding conservative current, which presents this conservation law. But now let me just start with a very general idea that if we have some object in a category and we have another object and we have a fixed map between them, then automorphisms of such a system are just automorphisms of the object X in the whole category, such that they preserve this classifying map. I mean, just a very general definition. Of course, this automorphism object may be quite complex, so it can be an infinity group or something like that, but the main idea is still the same. So the pullback of the classifying map along this automorphism should be at least equivalent to the initial classifying map. So morally, an automorphism is phi, where phi is an automorphism of the object X, and eta, where eta is the equivalence between phi upper star C and C. And the moral here is that if we apply this idea to prequantum geometry, then we will recover the notion of a classical symmetry of a system and some of its generalizations. So let's start from automorphisms of phase spaces. So assume that we have a phase space. Then an automorphism of a phase space is such a phi that phi upper star of omega, where omega is this canonical presymplectic form on the phase space, is preserved by phi. So that's the definition of an automorphism of phase space. Okay. then we can kind of that's an automorphism of phase space without prequantization. Then we can prequantize this notion, and instead of a form omega, which is sort of rigid and would require that the pullback is strictly equal to the initial form. So we don't have any equivalence, we just have the equality. Then after prequantization, instead of saying that the pullback should be equal to the initial form, we can, or in this case to the initial gerb, we can instead say that we want the pullback to be equivalent. And in this case, since this thing classifies Chapdelaine co-cycles, the condition that it is equivalent means that it differs by a boundary in the Chapdelaine complex, just in a Deligne complex, I'm sorry. So such a pair, which consists of an automorphism and a boundary inside of the Deligne complex, is called a quantumorphism. Well, somebody calls it a quantumorphism. And we can describe quantumorphisms concretely for some specific choice of the automorphism phi and a specific choice, for a specific choice of an automorphism phi, I guess, yeah. And under additional assumption that theta is a globally defined form. Globally defined co-cycle. So instead of this whole hierarchy of things, we just have a globally defined form. So assume that phi is a flow of some vector field V. That's an alternative notation for this. Then we have this equation which states that the difference between the pullback form and the initial form is a boundary of something. Then we can take the limit where t tends to 0, obviously divide by t, and we will obtain the following equation. So the Lie derivative with respect to this vector field of the form theta is equal to differential of some function alpha. Then we can apply the Cortan's formula to instead rewrite the Lie derivative as the sum, but we know that the differential of theta should be equal to omega, and this is equal to d alpha. Then we can rearrange the terms in this equation, and we obtain a function under the sign of differential, which should be equal to the contraction of omega and the vector field V. And this function under the differential is precisely the Hamiltonian of this vector field. Okay, so it turns out that quantumorphisms in this case are related to Hamiltonians of vector fields. So we have this pair consisting of a vector field and a Hamiltonian. So a vector field is an infinitesimal generator of our automorphism, and the Hamiltonian is precisely this element in the Deligne complex, to which we apply the differential and obtain the boundary which exhibits this equivalence between the pullback of the form along the flow of the vector field and the form itself. And so obviously, well, not obviously, but I guess it's not hard to deduce that the set of all such pairs has a smooth group structure. So it's a sheaf. It's a sheaf on the category of manifolds which has a group structure. I think, yeah, that's the proper description. And we have a Lie bracket on Hamiltonians, which comes from this smooth group structure. And we can explicitly compute the value of this bracket using the following formula. So assume that we have two tangent vectors to this group, which are constituted by a vector field and a Hamiltonian and another vector field and a Hamiltonian. Then we should take a Lie bracket on vector fields, and we should take a contraction of two form with these two vector fields. And if omega is non-degenerate, so it's symplectic, then this bracket coincides with the usual Poisson bracket on functions on a symplectic manifold. So as it turns out, the Poisson bracket on functions is nothing more than the Lie group structure on infinitesimal symmetries of a physical system, for which this manifold is the phase space. So we see this relationship between the Poisson bracket and infinitesimal quantumorphisms of our system. Okay. So, as I said before, if we have a symplectic structure on the phase space, it means that the smooth functions on this phase space with the Poisson structure coincide with the Lie algebra of the group of quantumorphisms of this form theta. In particular, if we have as a phase space the cotangent bundle of R, then, well, obviously it's R2. The form omega will be given by the standard form on R2, for which we will have, and then we will have the following bracket structure on smooth functions. So, in a sense, you can think of these two functions as free generators of C-infinity ring of smooth functions, and then this equation completely determines the Lie algebra structure on this ring of functions. So, in particular, we see that the value of this Lie bracket is a locally constant function. Well, in this case, it's globally constant, but doesn't matter. So actually, we have so actually it belongs to this I H bar R vector space, which embeds into the Lie algebra of into the Poisson Lie algebra on this manifold. And this gives us somewhat of an idea how, in general, the group of quantumorphisms or Lie algebra of infinitesimal quantumorphisms should look. So both Q and P are vector fields on the phase space. And as it turns out, Poisson Lie algebra is nothing more but a central extension of the Lie algebra of vector fields by locally constant Hamiltonians. And that's the general idea that may come to mind from this example. So we have this constant Soriano extensions, which are given by this. So we have vector fields on phase space. Then we have an extension of these vector fields by locally constant vector fields, or locally constant Hamiltonians. And we obtain the Poisson-Lie algebra structure. And similarly, for quantum morphisms, we have the group of diffeomorphisms of the phase space, and we just take the central extension with respect to the group with respect to this group, which is just E. One moment. Yeah, it's ER modulo EH bar C. Yeah, so we have this description of quantum morphisms and infinitesimal quantum morphisms, which are just symmetries of our system. And abstractly, this works as follows. So we have form theta, we have some, well, I guess gauge of this form, so transformation of the form into itself. Then we also have some automorphism of a phase space, and together they give us all possible automorphisms of this structure. So we have phase space here, some automorphism, and some equivalence between theta and theta on both sides. And yeah, that's the general description of quantum morphisms or infinitesimal quantum morphisms. Okay, so in the similar way, we can describe higher extensions where instead of Lie algebra, we have an L infinity algebra, and instead of just a group, we have an infinity group. Okay, so in this case, we have higher TS extensions, which look like this. So assume that we have some form omega, which goes from the space of solutions to something like this. And then we just require our infinitesimal quantum morphisms or our quantum morphisms to preserve this structure. Okay. So now I guess I'm already over time, so I will try to finish this quickly. So let me describe the relationship with the Noether's theorem. So consider a quantum morphism which preserves this early Lagrange prequantization of the early Lagrange form. Assume that also, let's consider a very special case where L is globally defined, and we have the automorphism given by a flow of a certain vector field. So a situation like this. Then the equivalence between L and the pullback of L is given by the exponent of the following thing. So we have a certain go chain in. So we have a certain differential form. I guess since it's globally defined, we can think that that's just a differential form. We don't need anything else. We don't need any complex code chains in the Deligne complex. And as I said, we can think of this thing here as being the boundary which exhibits an equivalence between the pullback and the initial form. Then after we take a limit with respect to t, we once again obtain an equation like this. Then we once again apply the Cartan's magic formula, and we rearrange the terms, and we see that here we get a difference of delta and contraction of theta large and v, and here we get the contraction of a Lagrange form with v. And since this contraction is zero, just from the fact that we've taken one moment. No, I'm sure that. Yeah. Okay. Never mind. The important thing is that this thing here is a conserved current, and the fact that it is conserved is precisely the essence of the Noether's theorem. So we have this infinitesimal automorphism, and precisely this quantity should be the, so to speak, conservation law, which corresponds to this symmetry given by a flow of the vector field V. So let's sort of prove Noether's theorem. So assume that we have a boundary of our space-time, then we have a commutative diagram like this, which is natural in E, meaning that if we vary our Lagrange equations, then the diagram varies accordingly, and we always have the appropriate shell here. We also have this condition on the conservation of the Lagrange gerbe, and then we can consider the transgression with respect to delta sigma, I guess. And what we will obtain is the following prismatic diagram, which, as it turns out, is equivalent to this diagram. So we actually can collapse this and this, and we'll obtain a triangular diagram like this. So our ability to make such a contraction, yeah, obviously I'm skipping a lot here, but our ability to make such a contraction means that if our space-time splits like this, then the difference between one forms on one side of the cylinder and on the other vanishes. That's why we can identify omega-1 here and here. And that precisely is the condition that we have a conserved current, meaning that its horizontal differential is zero, so it doesn't change when we vary over our space-time. And Noether's theorem can be formulated abstractly like this. So assume that we have abstract formulation of Noether's theorem states that conservative automorphisms which preserve our our equations of motion, so to speak. Well, not actually just the equations of motion, but actually they preserve prequantizations of their Lagrange equations, are obtained from automorphisms of the field bundle, which are centrally extended by topological currents, which are just automorphisms of prequantized early Lagrange equations, or in this case, early Lagrange gerbes on E. So that's an analog of the previous considerations of the fact that in general we can obtain quantumorphisms as extensions of automorphisms by our gauge transformations. Something like that. Okay, so now we can deduce from this that actually we have the following. So in the case of Lepage forms, which are lifts of Lepage gerbes, which are lifts of early Lagrange gerbes, if we take the Lie derivative of the corresponding form, we obtain precisely the Hamiltonian of this vector field, which in a sense gives us our observables. And if we take the Lie derivative of the early Lagrange gerbe, then we obtain the differential of this form, this current delta. And if we take, and from this we can recover the conserved current, which corresponds to our automorphism given by the flow of this field V. Okay, so finally, I promised a certain explanation about Lagrangian and isotropic correspondences and their meaning, their physical meaning. So let me just first recall a very basic fact that if we have a T+2 form on such a product, where sigma has dimension P, then the differential of the transgression of this form with respect to sigma is not necessarily closed, but we can apply the Stokes theorem to see that it is closed precisely when the transgression with respect to the boundary of sigma is 0. So sigma transgression is closed if and only if the d sigma transgression vanishes. Okay, that's a very basic thing about just very basic calculus. Okay, so assume that we have a presymplectic form on a phase space. This canonical, meaning that actually its horizontal differential is 0, so it doesn't change when we move around on the space-time. To see this, we apply the horizontal differential as we should. We remember that omega is actually a variational derivative of this form theta, which corresponds to a lift of omega. And then we can interchange the variation, the vertical variational and horizontal differentials. Then we can recall that the horizontal differential, this form, actually is supposed to be this thing. And then this term is annihilated, and we're left with the variational derivative of the early Lagrange equation, which is basically by definition 0. So that's basically the condition that our equations of motion are variational. So that the vertical variational differential should be 0. And now we can assume that our boundary of our spacetime splits as two hypersurfaces. So we start from somewhere and we end up somewhere. Then we can define two forms, which are transgressions with respect to the incoming hypersurface and respectively the outcoming hypersurface. And then we get an isotropic correspondence. So we have this phase space, and we have the restrictions to this thing here and this thing here, which are not quite phase spaces, but they give us configurations of they give us configurations of a field over this incoming hypersurface and outcoming hypersurface plus values of all derivatives. And then we have two forms, one on each of these spaces. So it is an isotropic correspondence, meaning that if we take a symplectic form on the product of these two spaces, given by the difference of the outcoming form and the incoming form, then this thing here will be isotropic with respect to this presymplectic form. And in the case when both incoming and outcoming surface are Cauchy surfaces, meaning that these maps are actually equivalences, it's not just an isotropic correspondence, it's a Lagrangian correspondence, meaning that it's sort of a maximal isotropic correspondence. So the moral of this part, I guess, is that if we have a certain transformation from an incoming surface to an outcoming surface, it corresponds to a correspondence between the respective phase spaces. So a phase space of the total space-time is a correspondence between the state of the system at the beginning and the state of the system at the end. That's I guess it's a very general idea that somehow the behavior of the system should relate what happened at the beginning with what happens at the end. And this is expressed by this square diagram, this rhomboid diagram, that after prequantization, meaning that we lift to this classifying stack, we get this rhomboid. So we start, so we have this field trajectories, and they give us correspondence between incoming field configurations. So we map here by taking initial values. And on the other hand, we have outgoing field configurations, which are given by mapping field trajectories to its Hamiltonian evolutions. And here, instead of differential forms, we have these classifying stack. And so we have a prequantum bundle, which is classified by a map into this classifying stack. So we have this correspondence, and that's the way that we prequantize Lagrangian correspondence from classical mechanics. We take the prequantization of each of these four things here, and we end up with something like that. So we have field trajectories, incoming field configurations, outgoing field configurations, and the classifying group of prequantized bundles. Okay. I guess that concludes my talk, and probably all this incomprehensive rambling about physics in general. And I hope that from now on we'll have some concise talks about homotopy theory, which are now motivated by some physical meaning behind all this abstract technique that we use to describe hyperphoria and do some geometry in them. Okay, let me stop the recording here.